Hi, my name is Brian Caffo, and this is the Introduction to Statistical Inference lecture in the Statistical Inference Coursera class. This is co-taught with my co-instructors, Jeff Leake and Roger Peng. We're all in the Department of Biostatistics at the Johns Hopkins Bloomberg School of Public Health. So inference is the process of drawing formal conclusions from data. In our class, we'll just define it as settings where one wants to infer facts about a population using noisy statistical data where uncertainty must be accounted for. I like to think of inference in this way. The sample mean, the sample variance, and all of these other things that we talk about, these data level quantities, are all estimators. If they're estimators, they must have estimands, things that they are estimating. What are those things? And we need a framework, a statistical framework, to make those kinds of definitions. Without it, we're merely talking about things within our data set. If we want to generalize or abstract or in any way use our data set to make conclusions beyond the data in question, we need to perform an inference. Here's a motivating example. Who's going to win the next election? And in every major elections, there are so-called pollsters who would like to know ahead of time who's going to win. So the target of estimation, the estimand, is clear. The percentage of people in a particular group, the percentage of voters, of people who will vote for each particular candidate. But we can't poll everyone, and we can't even determine who's going to go to the polls or not, even if they say they are ahead of time. And some people might change their vote by the time the election occurs. So how do we collect a reasonable subset of data and quantify the uncertainty in the process to get a good guess at who will win? So that's a famous example of a kind of statistical inference. Another recently quite famous example is the hormone replacement therapy story. So hormone replacement therapy was a widely accepted treatment for menopausal symptoms. And there was a clinical trial, which in the world of in biostatistical evidence is the gold standard, that contradicted the evidence about use of hormone replacement therapy and actually suggested it might have a negative impact. So based on a statistically based protocol, the study actually was stopped. Right? They couldn't even go forward with finishing the study because the evidence mounted up to the point where they felt like they couldn't ethically continue on the trial. But here's some of the inferential problems they were trying to answer. Is hormone replacement therapy effective for these symptoms that they're trying to treat? How long should we continue the trial in the presence of contrary evidence? And we want to make conclusions about one or two in the light of uncertainty. And here's some references. If you're interested in this topic, it's fascinating on a variety of levels. Here's some references that you can look at. ECMO is another kind of famous one in the world of biology and medicine. So this is extracorporeal membrane oxygenation treatment, a highly promising treatment in 1985. Now it's commonplace. For intensive care, neonatal intensive care units, and this is the kind of part I'm trying to highlight here. The ethical considerations led to a statistical randomization scheme whereby one infant received the control therapy, and I think it was 8 received the ECMO. And then they stopped the trial because the evidence after that one control subject was enough. And so Richard Royal wrote a nice review paper about this that is worth reading. Is in statistical science. It's actually, even though it's in a stat journal, it's actually quite approachable. But here's an instance where they were talking about the design considerations and the consequences of the design on the inference. And in addition, this problem goes into kind of ethical considerations because in this trial there was a lot of a priori evidence that the treatment was highly effective, and there is this so-called issue of equipoise in whether or not you can ethically perform a trial and give a controlled treatment when in a case like this. So all these are examples of kind of well-known and famous and important examples of statistical inferences. But let's kind of highlight some aspects of them. So they illustrate many of the difficulties of trying to use data to create general conclusions about a population. It's not an easy process, and we'll try and navigate some of these problems in this class. So among our concerns are, is the sample representative of the population we'd like to draw inferences about? Ideally, are there known and observed, known and unobserved, or unknown and unobserved variables that contaminate our conclusions? Is there systematic bias created by missing data or the design or the conduct of the study? What randomness exists in the data, and how do we use it or adjust for it? Here, randomness can be explicit via randomization or random sampling, or implicit as the aggregation of many complex unknown processes. Are we trying to estimate an underlying mechanistic model of the phenomenon under study? So we'll talk about that a lot in our regression class. So statistical inference requires navigating the set of assumptions and tools and subsequently thinking about how to draw conclusions from the data. So it considers all of these things, and these are all difficult topics in statistics, and all even could deserve their own courses or multiple courses in their own right. So some example goals of the kinds of goals of inference. So you might want to estimate and quantify the uncertainty of an estimate of a population quantity. So in our example, polling example, the proportion of people who will vote for a candidate. We not only want to obtain an estimate of that based on our study design, but we also want to quantify the uncertainty in that estimate. Determining whether a population quantity is a benchmark value. So is the treatment effective? Comparing treatment versus control, we want to compare that difference versus 0, for example. We might want to infer a mechanistic relationship when quantities are measured with noise. So what's the slope for Hooke's law is the example that comes to my mind. An interesting one, I think, is determining the impact of a policy. If we reduce population levels, will asthma rates decline? So there, we might actually want to average over kind of complex mechanisms. We're not so concerned about the explicit mechanisms by which asthma pollution levels relate to asthma. Instead, what we're more interested in is just aggregating over these this complex relationship between these two variables. Just if we adopt the policy of reducing pollution levels versus not, what would that do to change in asthma levels? It's a different question than understanding a mechanism, right? There we're just saying kind of we're happy to average over the mechanism. So some tools of the trade of inference. Randomization is a big one. And so what randomization is concerned with is you randomize a treatment or something like that. Randomness is great because if you randomize a treatment and you compare the treated versus the control, the groups are balanced with respect to unobserved variables that may confound the inferences of interest. That's the primary purpose of randomization. Random sampling is concerned with trying to get a data set that's representative of the population that you're interested in drawing conclusions about. The problem with two of these is many of the data sets that we deal with neither have randomization nor are randomly sampled. So instead of random sampling, often we have so-called sampling models. So we often assume things about the data regardless of how it was actually collected. We might evaluate, or hopefully we would evaluate our robustness of our conclusion to these things, but it's often the case that because we have no control over the sampling, we just make assumptions about the sampling process and use our model or our inferences as sort of a probe to diagnose things about the data. So sampling models are a good example of that kind of process. Hypothesis testing is concerned with decision making in the presence of uncertainty, deciding between two hypotheses or multiple hypotheses. Confidence intervals are closely related to hypothesis testing and are concerned with quantifying uncertainty and estimation. Probability models probability models, if you specify a full probability model, it is a link between your data and a population. The combination of a probability model and a sampling model is all that you need to infer things about a population. Study design is the process of designing experiments in order to draw inferences. Often you can, for example, if you're interested in a policy type effect, if you can randomize that policy, then that makes it very simple to investigate it. Just to take the average difference, and that you can get a quick standard error and do a very quick type of analyses. If you can't do randomization, then some sort of study design, other complicated, maybe more complicated study designs need to be pursued. So nonparametric bootstrapping is the process of using the data with a minimal probability model to create inferences. Permutation, randomization, and exchangeability testing. These are process of using data permutations to perform inferences. So the latter two, 8 and 9 here, are the idea of kind of data-based, data-oriented inferences. So we like those a lot in this series because we we're trying to be data scientists, so we like things that really make a heavy use of the data. Okay, here's a point that I'll bring up, but I don't want to belabor. So different thinking about probability leads to different styles of inference. So there are things like frequency probabilities, and there's even a little bit of wiggle room in how you define these things. But it's the long-run proportion of times an event occurs in independent, identically distributed repetitions. So think flipping a coin. We say that a coin has a 50% chance of a head because we think if we flip the coin a lot, the percentage of heads we get will limit to 50%. Frequency-style inference is related to frequency-style probability interpretations in that it uses frequency interpretation of probabilities to control error rates. So it answers questions like, what should I decide given my data controlling the long-run proportion of mistakes I make at a tolerable level. So that's frequency inference. You can see its kind of relationship with frequency interpretations of probability. Bayesian probability. Bayesian probability is the probability calculus of beliefs. And that, so it corresponds to if I believe this and then I update my my belief with this new probability information, what should I believe then? So Bayesian, those kind of probability calculations are the so-called calculus of beliefs. Bayesian inference is the use of Bayesian probability representation of beliefs to perform inference. And what I'm describing here, I would describe as a fairly narrow definition of Bayesian inference. Bayesian inference, in its modern incarnation, has kind of attracted a big tent idea of a whole variety of things that includes some amount of frequency thinking involved. So I don't want to spend too much time on this. In this class, data scientists as kind of practical people in general, they tend to fall within shades of gray of these and various other schools of inference. So, just kind of using the best tool that they can for the job, factoring in a variety of things. But it is interesting reading to read about the history of these things. So if you're interested in it, there's tons on the internet and tons of books and articles and etc. So in this class, we're going to primarily focus on basic sampling models without explicit randomization, random sampling investigated. And we're going to mostly focus on frequency style analyses. We'll also consider some inferential strategies that rely heavily on the observed data, such as permutation, testing, and bootstrapping. And then probability modeling will kind of be our starting point. And so we're going to first build up basic probability so you understand probability modeling. So I wanted to cover at least a little bit on where you learn more about these things that are not going to get covered in this class. So explicit use of random sampling in inferences. Any book on finite population statistics, survey sampling, is going to talk about how you can use explicit use of random sampling in your analyses. It'll also talk about how you can try, if you don't have a explicitly random sample, how can you try to overcome that? Then explicit use of randomization in inferences. Remember, random sampling was how you pick the subjects or units, and randomization is you're randomizing a treatment given whatever units, however you pick them. Randomization, there's this kind of relatively new discipline called causal inference that is entirely predicated on randomization, or huge chunks of it are predicated on randomization, and then clinical trials is very heavily uses randomization, and randomization in terms of its thinking. So Bayesian probability and Bayesian statistics, any basic introductory book. Missing data, probably the most popular missing data tool is called multiple imputation. But look up, if the missing data is well covered in biostatistics, econometrics, and so on. Study design is a huge topic, and I find that study design tends to be best covered in the subject matter discipline that you're looking at. So if you want to understand study design for kind of public health, look in the kind of epi literature. If you want to look at kind of classic agricultural study design, then that'll cover all the kind of block designs and things like that are also covered in the epi literature, maybe with just slightly different nomenclature and focus. And then the industrial quality control literature covers design very thoroughly. There's lots of different subjects that cover design. So what I would say is, if you're interested in design, read the books on design from the area that you're interested in applying design to.